any failures in the assignments, I've got to try and dig around and find out what you did wrong, so we can actually get you some credit for that. But I know it's difficult because we've got 3 assignments that are sort of outstanding, but try and sort of put that to one side for a minute. Okay, but that actually comes back to the fragility of these environments. So as we saw when we made our submissions for assignment 2 and 3, lots of the submissions, there were bits missing, the things that didn't actually work, and that's just what's the word? A result, a side effect of the way these development environments are put together. They're very complicated, and they are really very fragile. If you take the code from one environment and move it to somewhere else, quite often it won't actually work. So we have to try and figure out how we fix that. Similar thing with Swift, obviously different language, different tools, big difference in between Android development and iOS development. Android development is open source. There's lots of people who put input into it. Kotlin wasn't even developed by Google. Android Studio has taken on a life of its own. So there's a more active community. Downsides to those kind of communities is things tend to be a little bit hodgepodge. Some things work well, some others don't work quite so well. Whereas for iOS development, it all comes from a single company, Apple, and there is no other way of developing for iOS. You could, and some people do, but it's a lot of work. You could actually write the Swift in another IDE. There's nothing you can just, because they're just files on the disk. You can edit them in whatever IDE you like. But the feedback loop that you get from your previews only exists inside Xcode. And you need Xcode to actually build the apps that you've written inside some other environment. So although that Xcode is with us to stay, my non-scientific, review of it is that Xcode has got buggier as it's got bigger. So up until even 3 or 4 years ago, you'd rarely actually get an Xcode crash. They happen all the time using the very latest versions of the operating systems, the very latest versions of Xcode on modern Apple silicon. And I know many of you have had the similar issues when you actually come to office hours. But we're stuck with it. If we want to actually develop for iPhone and iPads and so on, we have to use Xcode. And so it's a captive market. So whilst I wouldn't imagine they deliberately go out of their way to have crummy products. It doesn't really matter, because if you want to deploy onto iPhone, and everybody does, and you want a native iPhone application, you have to use Xcode, or do you? So in a cross-platform world, what would be nice to do is say, actually, let's have a platform where we write the application once. So obviously, if we have an Android version of our application and an iOS version of application, there's very little similarity in the code base. Very little. There might be a little bit of shared functionality. The majority of the shared functionality will be in the API that we've written. Obviously, that's outside the scope of this class. Take 186 and 187 if you want to know how to do that, if you don't already. But the UIs that are actually running on the phones themselves are completely different. But it would be nice if we had an environment where we can actually write one app and it would magically work on both platforms, which are completely different. So that is cross-platform development. And the environment that we're going to be looking at here in 118 is React Native. It's not the only cross-platform development that's available, environments available to us. Flutter is also very popular. That's sort of coming up. I would guess that within probably a year, Flutter will have overtaken React Native. Works in a completely different way. The reason React Native is so popular is because it's the same language that the majority of sort of important and successful web apps are written in. So you can have the same code, you can share code in between your mobile app and your web app. And there's a significant advantage from an organization to do that. So some of the commercial organizations that I work with, they get up to 75% of their code is shared in between their mobile app and their web app because they're using React Native. Whereas if they were using Swift and Kotlin, they've got three completely different source code for three different ways of essentially doing the same thing. So if your mobile app and your web app allow you to achieve whatever it is the organization is allowing you to achieve, you've had to write it three times. And that is very, very, very expensive. So that's why React Native is popular. But as I say, Flutter is coming up on the outside. I think that it could easily overtake in the not too distant future. Okay, so we've got a number of things going on here. React Native itself, we'll see what that is, what React is and what React Native is. JavaScript, we'll also be looking at TypeScript. And we have a testing framework called Jest and a testing library specific to React Native, which is what this little owl here is. That's the React Native testing library. So the main difference, or big difference, so we had Kotlin, Swift, and now we've got JavaScript stroke TypeScript. So let's very quickly look at that. Just to sort of, you can do a quick show of hands in the participants. Those of you who've already done some work with JavaScript or TypeScript. Let's give us a wave. Yeah, in the participants. Yeah, quite a few. Good. Yeah. That makes sense. It's the world's most popular language right now. So, okay, good. All right, but not everybody. So we'll have to make sure everyone's up to speed with the right same level of understanding. Okay, so what is JavaScript? So it's a programming language. It's a general purpose programming language. It is not designed to be used for mobile apps. It's not designed to be used for web apps. It's designed to be general purpose. And it's very high level. So it's unlike C, which it has a very intimate relationship with the hardware. It's a long way distance from it. It's cross-platform, and it's if you wanted to write low-level code, JavaScript is not your guy. Interpreted, not a compiled language. So in order to be able to run JavaScript, you have to have a platform-dependent runtime. So the most common runtime for JavaScript is inside a web browser. But there are also interpreters to run on Windows, on Mac, on Linux, on you name it, on very small machines, on very big machines, and so on. So it's important that it's an interpreted language. So it's actually not, so JavaScript itself is not pre-compiled into anything else. It's actually executed as is. When we look at TypeScript, TypeScript is converted into JavaScript for us, and it's the JavaScript that's executed. So it's dynamic, although it's not compiled. It has compiler-like operations at runtime. So it does things within its runtime environment that would be done by a compiler for C or Pascal or Fortran or any of the traditional languages. So in terms of allocating memory for variables and assigning types and so on, but types is interesting because it is untyped or dynamically typed. Both are true. So any variable can hold any type of data. And you can't, in pure JavaScript, you cannot restrict the type of a variable. You can in TypeScript, which we'll look at in a moment, but you cannot in pure JavaScript. And although it's not true to say it's an object-oriented language, we can program in an object-oriented way because it has built-in what's called prototypes. So every object has a prototype. And if you think of the prototypes as being classes that the class of your object inherited from, you see how it's easy to program in an object-oriented fashion. So another important feature is what's called first-class functions. So in most traditional languages, C is a really good example. A function, we have our regular variables, data types, all of which in C are pointers to a piece of memory. And then we have functions, which are a completely different concept. Whereas in JavaScript, functions are first-class entities. So you can treat them in exactly the same way as any other variable or any other object within the system. So we can pass a function as an argument to another function. A function can return a function as its return type. It has Pascal calling convention, so a single object being returned from the function. we can change the code inside a function whilst the program is running. We can ask the function to tell us what its source code is, in the same way as we can ask a string to tell us how long it is. So functions are first-class entities in JavaScript, as they are in most modern languages, but definitely not in most traditional languages. And I should point out that there's a significant performance overhead for having that flexibility, which is the other side of the coin. Is that's why languages that were developed in the 60s didn't do that, because they wanted the as much performance as they could get by making functions not second-class entities, but a completely different style of entity. Okay, so in programming models, we can program in an object-oriented fashion using all the keywords that we expect from an OO language. Excuse me. Inheritance is generally regarded as being evil, so trying to avoid that in your own code. But encapsulation, abstraction, and polymorphism, definitely things that we actually want to be using. But code is it's imperative. So basically, code is executed sequentially. With some exceptions, if we see a JavaScript source code file, the lines of code in that file are executed one after the other, top to the bottom. So it's easy to understand. We're not jumping around a lot within the code, which makes sense when it's an interpreted language, because the interpreter will read it top to bottom and execute code as it finds it. So we can also program in the functional style, which this is the desirable programming style. We want to try and avoid actually being totally imperative. In other words, having a single JavaScript file being one long diatribe, top to bottom, no functions, just one line after the other. We want to break it down into functions so it's easy to understand. We want functions to call other functions. We have a call tree, go down the tree, back up the tree, rather than a big diatribe of imperative code manipulating a huge number of global variables. And we'll have a look at some examples of that in a minute. Although it has Java in the world, it's not particularly like Java. Both derived from C. C is the granddaddy of all programming languages that we use today, almost all. But very wildly different paths. And we'll have a look at similarities and differences in between C and JavaScript on a subsequent slide. But JavaScript is a mess. It's not an opinion; it's a fact. It wasn't even designed by committee like C++ was, which is also a mess. But it was designed almost by a million monkeys typing away on typewriters. It is enormous. It is contradictory. It is you can go down a rabbit hole in terms of some of the features it has, and make a whole pile of problems for yourself. I don't have a picture on it here, but there's a picture that I use in another class that has a huge thick book of basically the entirety of JavaScript, and then a much thinner one of basically the things that you need to know and you should use. So JavaScript itself is a mess. However, today we don't actually program in JavaScript. We're programming something called ECMAScript, which is the JavaScript standard adhered to by most, cross it out and say, effectively all browsers today. And although on cross-platform development for mobile phones, we're not going to be running in a browser, we should be following the ECMAScript standards, and we will be. So that tightens up some of the craziness of JavaScript. And a new version comes out every year. We've just had the new one. So it's also been, the initiative has been going on for some time. And it brings some sanity to JavaScript. It also adds some additional keywords that are not, strictly speaking, in JavaScript, like class, if we actually want to do object-oriented programming. So ECMAScript brings a lot of sanity to the craziness that is JavaScript. But again, don't forget that it's wildly popular. It is the most popular programming language in the world today, and has been for some time. There's a good reason behind that. It's because when you're writing a web application, you can write the backend, the API, and your front end, the UI that you see in your browser, in the same language. It's always a pain when you have to switch between languages. JavaScript basically won the programming language wars because it's the runtime environment for web browsers. Okay, so it is heavily based on C. So here's a little bit of C over there on the left. It's not a particularly interesting or useful bit of C, but this is the same thing in JavaScript. So if you just sort of glance at that, looks pretty much identical. There's some minor differences down. We have a main function in here. Down at the bottom, we don't, because the JavaScript interpreter reads it top to bottom. And when it gets here, it calls the function foo, whereas we don't need a main, but pretty much the same. So if we actually run that, if we compile it, the one on the left, same as C, and run it, at the end, we get whatever we get, not a particularly interesting result, until you do exactly the same thing in JavaScript. So Node runtime environment, we'll look at that in a moment, and we get a different answer. And the difference is because JavaScript has dynamic typing. So when we declare these variables here, dep, sum, and I, they are strongly typed to be integers. So they start off as integers, they stay integers, they will never change from being an integer. When you do something like this, multiplying by a floating point number, the C compiler will round the result so that sum always is an integer. And whatever the floating point part of that calculation is sliced off the end. Whereas in JavaScript, all variables, although they start as integers, 3, 0, and 0, when we do something like this, sum, instead of being an integer, becomes floating point. In JavaScript, there is no, what's the word? There are no types. It just becomes, if you were to ask sum and say, what are you? It would say, I'm a number. And it would say, I'm a number here, even though we know, in quotes, it's an integer. Here it would just say, I'm still a number. I just happen to be a floating point number. So the dynamic typing, we have to be aware of that and make sure it's with the code that we've written is doing what we expect. How do we know that? We test it. So a lot of you have already programmed in JavaScript, which is great. Those of you who haven't, it's no big. It's a very easy language. Its structures, its looping, its conditionals, and so on are as you would expect in any modern language. And there's what's the word? More example code of JavaScript out there than there is of any other language. But in order for us to be able to actually execute JavaScript outside a browser, which has a JavaScript runtime embedded into it, we need something that allows us to run it on the command line. So here we're using Node. It should be pointed out that Node is not the only command line JavaScript executor. There are others, but this is by far the most popular one. So it's a runtime environment for JavaScript on the command line. So we just in a terminal, Node, name of our JavaScript file, off it goes. It's multi-platform. It works just as well as on Linux, on Mac, and Windows, anything else you can imagine. And we rely on it to be well tested so that it works in the same way on all the platforms. And internally, although it has a fair amount of other stuff around it, it is Google's V8 JavaScript runtime that comes from Chrome. That's very convenient for the Node developers because Google provides V8 and they provide the wrapper around it to allow it to run on the command line, plus give it an ecosystem in which that makes it very convenient to use as a development environment. So we're using it for the cross-platform development. We will install Node. Our projects will be Node projects, but that's purely a development time construct. Node does not run on the phone. So we're using Node as the development environment. We will be writing in JavaScript, and we'll see what actually happens in terms of what actually gets deployed. Um, but then I said that we'll be writing in JavaScript. We can write in JavaScript. We should write in TypeScript. So as we saw when we compared the C and the JavaScript version of that very simple but not very useful program, the uh, dynamic typing or no typing of JavaScript does some interesting things. What we would like to do, and TypeScript was an initiative of Microsoft, is tighten that up and say, look, we love JavaScript, we love being able to actually do this web development and in the browser and in the server, but JavaScript is just a little bit too mad for us to want to do that. It's too risky. So TypeScript layers on top of JavaScript and gives us the ability to add strongly typed language to the features. But it's important to remember that it's a strict superset. So basically, any piece of JavaScript that you've ever written or are ever about to write is valid TypeScript. There are no JavaScript features that you're not allowed to use in TypeScript. TypeScript adds features to JavaScript. The idea being to make your life easier, or more, possibly more accurately, to make it less likely or less easy for you to make a mistake that lies sort of dormant in your code for some time and then come back to bite you later. So it has this. I maybe should have put compilation in quotes there. So when you write TypeScript, it actually gets converted into JavaScript before that gets sent to the JavaScript interpreter. So either in the browser, or on the server, or inside Node. Excuse me. So it basically has a whole bunch of syntactic sugar that is telling this compiler, this converter, what it is you're trying to do. So you can tell the TypeScript compiler that I would like this variable to be of a certain type. And if anybody tries to assign a value to it of a different type, that will be a compilation error. In other words, when it's converting from TypeScript to JavaScript, it will fail. It will say, you tried to assign a string to a variable that you asked me only ever to be a Boolean. And you say, oh, yeah, great, and you fix that. Whereas in JavaScript, they say, that's fine. If you want to assign a string to a Boolean, fill your boots. So the aim is we want our code to be consistent, less likely to have type mismatches, type errors, which is why obviously it's called TypeScript. But we can write both in the same app. So if we write pure JavaScript, which we can do using when we're using React Native cross-platform development, then what gets deployed or what gets executed is just a copy of that written code. And if we write pure TypeScript, we compile it into pure JavaScript. And the most important bit is the last one, where we can have mix and match. So we copy the JavaScript and we compile the TypeScript, and we end up always with JavaScript. Okay. So we have some challenge. What are the JavaScript challenges that TypeScript address? So let's take this very simple example. So we've got a JavaScript function. This is one way of declaring a function in JavaScript. There's another way which is called arrow notation. But this is a function. So remember, foo is a first class object in JavaScript. So we just take an argument to the function that has no type. And the function doesn't declare anything about its return type. So we don't actually know the type of bar, but we're kind of assuming or hoping that whoever calls this function is going to pass as a string or maybe an array, and we can get the length of a string and we can get the length of an array. So if you pass it a string, it's going to tell us the length of hello is 5. Notice that that doesn't include any \n, as we wouldn't see. If we pass it an array, not a problem. It's going to tell us the length of the array. And if we declare a variable, val is an immutable variable that has an undefined value. So if we then pass it into foo, val that we're passing in, so val.length doesn't actually mean anything. So when we execute this code, the JavaScript interpreter will say no such thing. There is no length attribute of a variable that has an undefined value. So the variable exists. It's not null. It's not a zero-length string. It's not nil, as we've had in other language. It's just undefined. We don't actually know what it is. And its type is also undefined. But we don't know that until we actually execute this line. So sort of roll that forward a little bit. When we're writing pure JavaScript, it is really, really important that we have 100% code coverage. Incredibly important. Because these kind of problems can be lying around latent in our code. And unless we've actually executed every single line, we don't know whether or not we might bump into one of these at runtime. And we don't want that to happen in our deployed applications. So TypeScript is designed to solve exactly this kind of problem. So if you write the same thing in TypeScript, here we've got function foo, says nothing about the return type. So it's essentially saying we're going to return nothing. But we have the ability to say we have the ability to give the type of bar in the argument declaration. So it's still bar, colon, and then string. So we're saying bar must be a string in order for this code to compile from TypeScript into JavaScript. So if we call it with hello, we're going to get a 5. Perfect. If we call it with an array, the compiler, so before it actually gets to JavaScript, is going to say you cannot do that. So basically it's saying that 1, 2, 3 is an array of number, which it is, which is not a string. So you're not actually allowed to actually do that at all. Oops, get back in here. However, maybe that's not what we want. Maybe the previous functionality where we could give it a string or an array is what we want. So are we now restricted from doing that? Can that not be something we can achieve in TypeScript? Well, remember that TypeScript is a strict superset. So anything that we can do in JavaScript, we must be able to do in TypeScript, and we can. So we actually want a situation where we can do both, where we can get a 5 when we pass in the string, and we can get a 3 when we pass in the array. And we can do that by saying that bar is a string or an array of numbers, in which case both of those will work, which is exactly what we want. But importantly, this one will not work. The compiler will complain about that, excuse me, because val is not a string and it's not an array of numbers either. It's undefined. It doesn't actually have any kind of value attached to it at all. So in TypeScript, which you should be using, we have type annotations. So here we've got variables, and we have constants. And so constants, a convention is not required by TypeScript. It should be all in uppercase with underscore case, whereas variables should actually be in camel case, starting with a lowercase letter, and it comes after the type. So we have some examples here. So age is of type number, and its initial value is 20. Alphabet is a constant string, obviously a function. It takes a divisor and a dividend and returns a Boolean. Yeah, so does this divide that? Obviously, if we don't, and so this bit here at the end where we say colon Boolean, this is the return type, and obviously just the empty squiggly brackets here just means there is actually no implementation, just so it fits on the slide. Excuse me. But TypeScript also has type inference. So we don't need to declare in advance what the type is. So on the first one, foo, it has an inferred type of string because that's the initial value we actually gave it. So both of these cases, foo is mutable. You can change its value. So basically, they're exactly the same. Whereas these are not. because the inferred type of foo is number. So in TypeScript, there is no integer type or float or double. Everything's just a number. Whereas here, on the second one, that will throw an error because one is not a string. TypeScript says, why are you telling me it's a string when you're actually assigning its value to be a number? I don't understand what you're trying to do on the compilable file. So the primitive, the everyday types that we use all the time in TypeScript, there aren't very many of them. There's only number, string, Boolean. Those are the real ones. And null, which doesn't mean the same as null does in many other languages. It's a special value that you choose to mean whatever you want. It doesn't actually mean anything to TypeScript or JavaScript, whereas undefined absolutely does. It means something, either the type or the value is undefined. So if you declare a variable in TypeScript to be a string, and you would say type of the variable, it would come back and say string. And then you set the value and say, what is the value? And it would say whatever string you assign to it. If you then set the value to be undefined, the type is still string, its value is undefined. But if you declared something like, let me go back to the previous one. If we just said let foo, semicolon, no initial assignment, its type is also defined until you do an initial assignment. But obviously, we build on top of those with arrays. So in TypeScript and JavaScript, the most common collection is an array. So we can either say the type, so this would be Boolean or string or number or something, or an array, which is a built-in class within TypeScript. And then sort of one step up from those, we have the non-primitive types. So an object, so an object is implicitly something that is a composition, a collection, a set of primitive variables of primitive types or other objects. So an attribute of an object is either a primitive type or an instance of another object. So functions, they're first-class entities, but they're non-primitive, but they are objects. And then we have this any, this is a special type that can represent anything. Be wary of any. It can be useful when you're trying to work out exactly what the type of something should be. But once you've figured it out so that your code actually runs, and then once you've actually figured it out, you then tighten it up to be whatever either the non-primitive or primitive type that it actually should have been. So it's handy, but also dangerous. Code quality checkers will reject anything that your code that actually still has any lying around in it. It's their intermediate step. Okay, so if we want to generate objects in pure JavaScript, we just say, let my object become equal to, say, curly brackets, and then we just define a whole bunch of name value pairs, which is fine until the system gets a little bit complicated and we actually want to say, actually, no, it's not just a collection of name value pairs. We actually want to define it up front and say this thing is a whatever. And we can do that through interfaces. So, but you cannot create an instance of an interface. You can create instances of objects that implement that interface. So they have no functionality in their own right. So these are like data classes we've seen previously in the other two platforms. We're laying out a table or a protocol in Swift, data type in Kotlin and a protocol in Swift. So basically, here's the property, and this is what type it is. So as an example, we could say we have a point, two-dimensional point, where x and y are both numbers. Excuse me. So we can actually have, we can also have function annotations. If we want to have, what's the word? We want to say an interface has not only attributes, but also has methods. So this is object-oriented speak here. So basically, here's an interface again, and it has a function. It's called func. Type, it has two parameters of two different types, and it has a return type. So here, a button has a title of string, so that's an attribute, it's a data value, but it also has an onPress function. This arrow syntax allows us to be a little terser, and it returns void, which means this function doesn't return anything. So you shouldn't expect to assign a value to the return of onPress. If you do, it will just have a value of void, and its type would probably be undefined. I'm not quite sure about that. Okay, so that's functional annotation. So we can actually do map annotations on an interface as well. So here, this one actually we have a key. Uh, the square bracket syntax here is saying what is the type of the key and what is the type of the value. So an example, a phone book, the key is the name. You put in Dr. Harrison and it returns a string, which would be my phone number. So phone numbers obviously are not numbers, they're strings. Okay, so TypeScript is the next step up. Most examples you find online these days will be TypeScript. Try and avoid programming JavaScript unless you really have to. We'll see some examples where we mix and match just to prove the point. But in order to use TypeScript, so a node project is a JavaScript project. End of story. But in order to use TypeScript in our node projects, we need to tell a node environment what to do. So for instance, this is not an example we'll be using, but if we have a node project and the in the package.json, which is the definition file. So we've seen in Android, we had some quite complicated definitions in lots of different files all over the place, and Gradle doing its craziness to pull things together. And in iOS development, we had the XC package, which I'm sure most of you figured out is actually not a file. It's a folder structure that contains lots and lots of configuration files. So in Node, we have a single configuration file, package.json, which can include others if we want to get complicated. But we're basically telling Node all the third-party packages it needs to be able to do whatever it is we're trying to get it to do. So here, if we're using Postgres as a database, that's fine, the top one, so long as we're using plain JavaScript. But if we actually want to use the TypeScript interface to Postgres, we need to tell it this is actually what we want. So we have to, as a dev dependency, not a runtime dependency. So this is code that would be bundled with the thing that we deploy. As a development dependency, we have to tell Node that we're going to write TypeScript for when we access the Postgres database, and it must understand the syntax for that. But for TypeScript, we also need a configuration file, tsconfig.json. You won't need to set these up for any of our projects, but they will be there because they've been provided for you, which tells the compiler what to do. So here, this is ECMAScript 6. So this is saying, we're currently on ECMAScript 15. This is saying, I want you to target a very old version of ECMAScript. You could easily be doing that because you're targeting some very old browsers. And strict, obviously true, you want to be very, very strict about the language definition. So you'll see these when we look at examples and download the starter code for the next assignment. Okay, so we got JavaScript, bit of a mess, not type-safe. TypeScript tightens that up, but we need to extend. Node is our development environment, our runtime environment for JavaScript, and we need to tell it that we're actually going to be using TypeScript. And obviously, the thing that we need to get the user interface is React. So React, not React Native, just React, regular React, is designed for web applications. So if you've taken 1.6 or 1.7, we'll have done a lot of React. And it was designed for getting, by Meta, actually they were still Facebook at the time, for getting snappy, quick responses when running in the browser. So in their own apps, they noticed that they were getting a bit sluggish, and they came up with React. It's a JavaScript framework to allow them to have snappier response in their web applications. It uses the model view controller. So the model is our data. The view is the thing that we're seeing. Whenever the model changes, what we see on the screen changes. So the thing that would prompt a change to the model is the controller. If you're not familiar with MVC, just do a little bit of reading up on that well-respected, mature programming pattern. So very important aspect of React. Minimal, if any, server-side report required, because React applications, the JavaScript that is generated from a React application is just a file, or potentially a number of files. And so any web server that can send that file to the browser can host a React application, because the React application is actually running in the browser. It's intended for large-scale single-page applications, which is basically everything that we use today. The web version of Slack, that's a large-scale single-page application. Slack's not written in React, by the way. And it has a whole bunch of modules, third-party components that we can bring in to use and make our lives easier. We can get things done more quickly. And this last one's really, really, really important. It has built into it testing hooks, so that it's very, very easy to test React applications, which we'll find very, very handy, and especially when we compare it to how we test in React compared to how do we test in Swift UI or Android and Kotlin. It's called React because it allows us very easily to react to changes in state. So we've seen, for instance, in our iOS applications, we had the state annotation to tell us something was state, and when we changed the value of a piece of state, that actually appeared, and our UI could trigger off that change in state. So React's push in that direction predates Swift UI's ability to do that. So everybody's realizing that this is a good idea. We actually have state variables. Our UIs react to changes in those state variables. That's why it's called React. But remember, testing hooks. Go on to those in a minute. So we write JavaScript or TypeScript, and we can write it in a fairly low-level fashion to manipulate the visual entities. Or we can take it up a level into something called JSX or TSX. It's really still JSX, JavaScript XML, but we can write TSX to generate JSX. And it is a language extension. It's not a, what's the word, a wrapper. It's not a separate language. It's not a preparser. It is a language extension to JavaScript. And it's how we define user interfaces in React. So it is akin to the declarative programming style that we have in Swift, Swift UI. It's a bit like a templating language, but it's more akin to the Swift UI style of programming. But for those of you who are programming HTML, it looks like HTML, but it's not. So here we have a piece of fairly standard JavaScript or TypeScript. So constant. So this variable is invariant; it will never change, and its value is hello world inside a first level header tag that looks like HTML, but this is not actually HTML. It's something that will eventually, if you're using React in the browser, which you still are, React up here, not React Native, will produce HTML and JavaScript that will manipulate it. But it's although the tags have the same name, it's not actually HTML. When we declare our own JSX types, we can use those as tags as well. Very powerful language, and we'll see some examples of that of this in a moment. So, but React is for browsers. React Native, so it's going to generate HTML and JavaScript to run in the browser. Excuse me. React Native is so cool because instead of generating HTML from our JSX, it generates native components for whichever platform we're targeting. So if we say we want an entry field, and we choose to render it for iOS, we'll get an iOS entry field and buttons that look like an iOS application. And if we compile it for Android, we will get genuine Android components. So this is why it's called native. So we write JSX, which is an abstract, high-level extension to the JavaScript and therefore TypeScript languages. And the React Native build environment will look at what we asked for and generate the correct component, the native component, for whichever platform we asked for. So this is React Native. So we write JSX, we write TypeScript or JavaScript. React Native does all the magic to convert that into whichever components we want. So if we write a single React Native application, just by telling the compiler which way to go, we get two different applications that do the same thing. So once we've tested them to prove that they do the same thing and that we haven't messed something up. Excuse me. So in development, so there's two stages to this. There's actually generating the deployed application, and there's generating the development version of the application. So if you were paying attention as we're going through Android and iOS, we never actually built a deployable version of the app. In other words, a deployable version that we could put into the Google Play Store or whatever it's called, or the Apple Store, App Store. We were always just doing it locally as a development build, pushing it to the simulator. I don't know whether any of you actually tried pushing it to your own phones, but it was still a development version. It was not an App Store version. So we'll be doing the same in React Native because it is challenging to get things deployed in the stores, to say the least. And this uses a third-party product called Metro, which will do all the bundling up for us and will communicate with the simulator, either iOS or Android, excuse me, so that we have a nice feedback loop when we're developing. So in React Native, there are no previews. There's no, we can't look at the UI we're developing until we actually push it to a simulator. But Metro allows us to have live feedback. We change the code, what we see in the simulator actually changes. And React Native is widely adopted. Almost anybody you've heard of uses React Native somewhere in their organization. It doesn't mean that the thing that you see is their storefront, their prime app or whatever is using it, but internally. And again, it's because it's React. So most organizations are using React and TypeScript for their web applications. So it's really easy for them to use React Native for their mobile applications as well. So let's look at how we given that we want to react to state, let's actually have a look at how we do that. Excuse me. So let me just publish into the Google Drive an example for you. You're ready to go to the right place. Yeah. Okay, so going in there should be something called 12.useStateHook.zip. Don't worry about installing it yet. It's more about poking around inside the code. Okay, someone give me a thumbs up in the, let me know when you can see that. 12.useStateHook.zip. Okay, go on, thumbs up, it's there. All right, so just to unzip that and then just open the folder in VS Code. So unless you have a particular preference for some other development environment, but VS Code is a good one. Okay, so the file that we want to be looking at is in source/UI React use state hook view.js. Someone give me a thumbs up when you found that. And notice this is a JavaScript file, whereas if you can see the app.tsx at the top level, that's a TypeScript file. This is done deliberately so that you can get the hang of being able to mix and match in between TypeScript and JavaScript. Okay, everybody got that open? Anybody just wave in the participants if you're still getting that going. Not much feedback there. Okay, so we'll carry on. Okay, so this is in the React use state hook view.js in the source/UI folder. Obviously, those of you who've done React before, this will be you'll recognize this. So these are what are called functional components. So this is JavaScript. So constant. This cannot now be mutated after being created. So React use state hook view is a function that accepts no parameters. The arrow syntax here basically saying in between these top and bottom curly brackets, this is the definition of that function. And the first thing we do, we're actually going to use react.useState. So we have a single piece of state. Well, let me just actually show you the application running. Oops. Let me get my. There you go. So this is the application actually running. So we have a single piece of state. Oh, go away. Single piece of state. This is obviously running in the Android simulator. Oh, on that point, all the React Native applications will do will be targeting Android only. So that if you're a Windows or a Linux person, you don't need to keep using the borrowed Mac. Everything we will target will be Android. But remember, we could target iOS as well. And you're more than welcome to do that. Just for a bit of interest, if you're a Mac person. But remember, or advice would be not to experiment with that until you've got the Android version working for the assignments. Okay, so we've got a single piece of state. Let me move that down here. And it's going to be monitoring what we type into here. This is the same example as we've seen on previous platforms. So here, for those of you not familiar with React, this return statement is the JSX, and this is JSX because it's a .js file that is returned from this functional component. So the every React component, true for React Native as well, has to return a single JSX component. So that view that's terminated here is the single component that's being returned. It can contain as many components as it likes. So this view, which comes from React Native, so it's a React Native view. So what React Native will do is say, okay, you want a view? Great. And what platform are you targeting? Oh, you're targeting iOS. It will actually create a Swift UI view for you. What platform are you targeting? Android. Okay, I'll do whatever I need to do to make that happen. And then inside it, we actually have a title, which there's some styles beneath it in the code that we have in the example. And then inside that view, we have a piece of text that says React use state hook, which is obviously coming up here. And then we have a text input. We're going to type something in. And then we have a text that's just going to display some information we can't actually type into it. If I click on it, I'm clicking it in the live app. It's not doing anything. Excuse me. So we have some style. Okay. So basically, the initial value at line 23 is whatever the initial value of the state variable here is. It obviously has no initial value, so the placeholder is visible. Oops, go back. No initial value, so the placeholder is visible. Accessibility label is input with a lowercase I. Yep, see it over there. If we'd given it an initial state that was something more interesting than a zero-length string, that would actually display in this text to input field. But the important bit, so basically here's our state variable, and here's what's called a synthetic mutator. So basically set input is a function that will be generated for us by React and we can actually then call to set the value. Okay, so so over here we have, oops, next one. When the input changes, so basically when the text inside the input field changes, this JSX component, text input, will call set input, passing it whatever the new value of the text is. And as a consequence, this text label at the bottom, it's not a label, it's a text field down here, will change. So if I type in, we've got the feedback that we've actually seen in previous examples from the other platforms. And it's not, it's the on change text handler that we care about here. We're not listening for key presses. So if I go into here and get rid of that, it's whenever the text changes. If we copy that and paste it in, oops, paste it in a number of times, oops, I didn't mean to do that, come back. Yeah. Yeah, we can do whatever we want, and we can paste things in and so on. But the important thing there is that's not a particularly interesting piece of code. The important thing is that it's React state that's doing that, same as when we're using a state variable in Swift UI. Excuse me. So as we saw, so we've actually got, notice that the value is also the input. So whenever it changes, the thing that we display is the new value as well. So as we saw, we could type it in. As we type it in, text appears here. Obviously, you can tell what assignment 7 is going to be. We're actually heading in the same direction. So let's actually go and actually have a look at slightly more complicated example, which will be our usual infix calculator. So let me just put that in there in the share 12.infix calculator. So give me the old thumbs up when you can see that. I'll bring that up in ADP as well. Let's get to the right place. Building an example. One of the things that you'll notice is doing thinking about it. There are a lot more steps. Hang on a minute. The distance in between the code that you write and what actually runs in the emulator is significant. Because it has to go from, you're writing JSX or TSX, which then has to go down to TypeScript, which then has to go to JavaScript, which then has to be, when React Native has to work out the native components for it to render for you. Okay, so this is the infix calculator running in the browser. If you were to bring the code up for that, if we actually have, let me just share this. Get rid of that for a minute. Change the size of that slightly. So here's our usual infix calculator. It's deliberately only partially implemented. Obviously, this is going to be the basis of your postfix calculator in assignment 7. Usual thing, we have a logic class, which is the one that's actually doing the calculation, and we have the visual class, that we're actually going to see on the screen. So see, oops, and here the only operators it supports are plus and minus. So if we do 1 plus 1, going to evaluate 1 minus 2. See your value on that. That's easy peasy. You do something in there. Got an operator. And obviously we can clear it, and away we go. So the infix calculator, that's, again, you've done it twice already. Shouldn't be any problem at all to convert that into JavaScript or TypeScript. Notice this is JavaScript. And then the view, which is the one we care about. So the app.tsx, this is a recommended approach to where things actually should be, is that the app.tsx is really just setting up this safe area view, which is a React concept. And then it dives straight into whatever the first view in your app is. So in your assignment, your app.tsx, which should look very, very similar to this, it just creates, in your case, it will be creating a postfix calculator view. Excuse me, and obviously you'll have a calendar view as well. So again, we've got an infix calculator view, which is a functional component. It has two pieces of state: the expression that we type in, whatever we put into here, and the result that comes back. Oh, the question there, yeah, modularity, absolutely, yeah. So we want to separate our componentry from the infrastructure that actually makes them work. Excuse me. So the infix calculator view shouldn't know where it is on this screen. So the app could say, I want to put an infix calculator view, and then directly underneath it, maybe I want to put another one. And then we get 2. Yeah, you can do that again. Get rid of that. That's a really good example of how quickly it re-renders in the simulator, by the way. Yep. But it would never be the infix calculator view's responsibility to say the app needs 2 of me. That's someone else's responsibility. Yeah, put that in. If we want another one, we can quite happily do that. Yep. So golden rule in any programming is each component that we write should do one thing and do it really well. So here our infix calculator is being really good, if really simple, at being an infix calculator. It knows nothing about user interfaces. Our infix calculator view is being really good at showing that on the screen. It doesn't actually know how to do a calculation. So modularity, each component does one thing very well. Obviously, this thing knows that there is a buddy of his that he can call to actually do the calculation, but all he's concerned about is doing the layout. Okay. So here's a good example of actually, if we put something in here as a 1 plus 1, evaluate, we now have both pieces of state are set. The expression is 1 plus 1. The result is 2. And here, what this function is going to be called when we press the clear button. You can see there's a button down here. Yeah, has a label of clear. That's an accessibility label. I'll show you title of clear. Now notice the title is CLEAR in camel case. Android standards in Material UI are to have all buttons in all uppercase. So it gets converted to all uppercase. Whereas if it was on iOS, the standard is to have camel case, so it would actually be displayed in camel case. Excuse me. So one of those things, it means that the accessibility label needs to be accurate so we can trigger off that in our tests, which we'll come to in a minute. So when we press this button, it calls the clear function, which sets the 2 pieces of state back to being 0-length strings. As a consequence, we have the value in here, the value of the expression, and we have the value of the result in here. So they change. And we don't have to write any code to make that happen. It just happens because we declared these pieces of these variables as state variables rather than just regular program variables. Obviously, you can have regular program variables, but remember that when you change their value, the user interface will not react to that change because they're not state. So anything that you're rendering on the screen should be state. Anything that you're just using as a utility variable should not be state, because we don't want to add in all that triggering to that. Okay, so so there's the example of the infix calculator. Obviously, you've got that at your disposal. You'll be using that for inspiration for assignment 7. But what's really interesting about the infix calculator example are the tests. So whilst we're looking at the slides, feel free to poke around the underscore tests folder. So just bring that over here again. So basically this folder at the top, we got 2 logic and UI, same as we had in Swift UI. Obviously, these are the tests for the logic. These are the tests for the user interface. So tests for the logic, very easy, but we're using the Jest testing environment or test framework. But if we, which we'll show examples of in a minute, that's fine. We just use Jest, which is this, Jest as shoe over here. That's fine for just testing regular JavaScript or TypeScript. But if you actually want to test React Native components, we need to have the React Native testing library, which is this guy over here, the OWL. And this is a really, really important bit. In order to run your React Native tests, you do not need the code to execute in a simulator or on a real phone. This is massive in terms of the ease with which you can actually run your React Native tests. So if I just bring up another terminal. Okay, so bearing in mind that the simulator is still running, so we've actually got the live version of the application is running over here. We're quite happily playing with it. So to run our test, we just do npm test. npm is the node package manager, and we just to get it to run the tests. And the tests that it will run, show you examples of them on the slides in a minute, do not run in the simulator. They run in something that's called a virtual DOM, which just runs on your laptop. So we get in the coverage, and what do we notice about that test run compared to test runs in the other environments? Anybody shout it out or stick it in chat? Again, thinking you'll miss it. So what do we like about that test run compared to the test runs that we had for our assignment 4 for iOS? It's lightning fast because it's not running in the simulator. It's running on your Mac or your Windows machine or your Linux machine. So it's a huge, huge, huge difference in terms of how we actually test our applications. So those of you who are getting towards the end or have already finished assignment 6, it takes a long, long time to run all those tests. Because every time you have to deploy a new version of the iOS application to the iPhone simulator, it actually runs in sort of human time. You're typing things in and clicking and coming back. And if you look at the resource utilization on your laptop whilst you're running the test, it's massive. So if I just share what my CPUs are doing when we run these React Native tests, they don't even get out of bed. Whereas if you were doing that for your assignment 6, all of my CPUs would be absolutely running red hot. So big sell for the mechanism for testing in React Native. So we're using Jest as so basically Jest is the testing framework. The React Native testing library is the thing that allows us to manipulate a React Native application. Excuse me. So basically here we've got this is our infix calculator tests. So this is Jest, pure Jest code. There's no React Native testing library here. So we're expecting it. So we basically create an instance of the infix calculator. We evaluate the expression. This is what we expected the result to be. And expect is a Jest primitive. It's the assertion, or one of the assertion syntaxes in Jest. So we expect the result we got back to be whatever we were told to expect. And that's code taken straight from an example. You can see the function that actually invokes it. Excuse me. Whereas if you actually want to test the JSX component, so we have our JSX component in the infix calculator example is the infix calculator view. We can do that by including from here at line 9, we import a number of functions from the React Native testing library, and we import the user interface view that we want to see. And then in our test here, so it and test are two different ways of declaring a test in Jest. So if you read this, including the it evaluates a simple expression. That's what we're testing. Does it evaluate a simple expression? A better one might be it evaluates a simple addition. Might be a better name for that test. But line 14 is the important one. So that the visual thing that we want to render is an instance of the infix calculator view. So render comes from the React Native testing library. So we render that piece of JSX. This is JSX inside here. We're creating an instance of this view. Excuse me. And then this is a compound statement. So basically screen, what we see on the screen, get by label text, which is getting it by its accessibility label of expression. Yeah, if you put back to the previous slide. Oh no, didn't. So I was doing that live. You can see that in the JSX for it. So we have an accessibility label and or a placeholder. So if we look in here, see where I mean. Excuse me. Oh, no, I want to look at the real one. I'll give you. So we have an accessibility label of lowercase expression. Yeah. So in our test, we get hold of it by label text expression. And then we pass the result of that, which is a visual view that we can see, into the fire event, which comes from the testing library, and we want to change the text. So we're going to change the text in that field to be 1 space plus space 3.2. Oh, this is floating point, by the way. Yep. Come back to the code coverage question in a minute. And then once we've typed that in, we then find the evaluate button. So again, come back to our on here, which is this guy down here, this button, because it has an accessibility label of evaluate. So it's going to find that button. Come back to the slides. And it's going to press it. Oops, go back. It's going to press the button. So now we've done two things. So this is a classic, good example of a test. We create something. Here we're rendering a view. We manipulate it. So we type in a bit of text and then we press a button. And then we assert something about what changed. Hang on a moment. I've just spilled my coffee. Just hang on. All right. And then we need to assert something about what changed. So what changed, or what we're expecting to happen, is that the 4.2 is going to appear on the screen. So obviously, if we do that by hand, what did we say? 1 plus 3.2. So we've found this thing. We've typed it in. We found the evaluate button, and we're going to click it. And what we expect to appear on the screen is the 4.2. So what I just did there by hand is the human interaction version of this test. So all your tests should look like this: render something, manipulate it a little, assert something to be true as a result of that manipulation. Excuse me. All right, has a question in the chat about cocoa. Right. Okay, so let's go and look on here. So when we ran the test, I'll just do it again. npm test. It produces your code coverage report. So it tells you after each test run what the coverage is. And obviously we want to be 100% on everything. Excuse me. It also produces in the, let me show you one here, coverage. It also produces you can open that in a browser, show preview. It also produces a pretty HTML version of it. Yeah. So if we didn't have 100% coverage on here, you could drill down on it and it would tell you where it was missed. But here, everything is green because we've got perfect code coverage on this one. Yep. So that's in your coverage LCOV report index.html. That gives you a much more detailed view of the code coverage. Yeah. So again, that's another upside of using React Native for cross-platform development, is it comes from a world, a web development, where everybody is rightly obsessed about code coverage. So it's right there. It's really easy to do. We compare that to, but we couldn't do it in Android Studio because it's not part of Android Studio. Okay, so if you were to initialize a React Native project, which you won't need to do because you'll get it as your starter code, use npx as the node package extension, create it for you. But importantly, you actually have to run, you choose which one you're going to do, run Android or run iOS. The instructions for those example projects and the assignment 7 are slightly different because we'll actually start two different processes. You will need to start the system that is allowing us to go back to this slide. So remember we had Metro. We actually need to start Metro up, and we'll do that in one window, which will connect to our simulator. The simulator needs to be running, by the way. So you'll go into Android Studio and get the simulator running. Excuse me. You can then close Android Studio if you want, as long as the simulator is running, and Metro will happily connect to it. If the simulator is not running, Metro will not start one for you. So you have to have the same one as we used in the Android assignments up and running. Yeah, okay. But so this slide is just for information. We won't actually do that. If you want to delve off and create one of your own, go ahead, but we don't need to do that for the assignment. So lots of resources online, and the ones for the React Native testing library and Jest, if you've not used those before, those are the most important ones. Okay, so let's go and have a look at assignment 7. So actually, whilst we're doing that, let me just go and run that up and close the examples down, get that running whilst we wait. Startup bit you'll find when you actually install these things is a little bit what's the word? It's slower than when it's actually running, but once it's actually running and you see it in the simulator, you get an almost instant feedback from Metro when you change the UI. Okay, so obviously postfix calculator. There's a class that's built in. Don't change the signature of that function. couple of you made that mistake in earlier assignments. The known good tests require that to be there, so don't change them. And obviously, so we have postfix skeleton, obviously a postfix calculator view. So tests are provided for these. So you've got some tests to actually have a look at, excuse me, and use as inspiration for the next bit, which is obviously your calendar generator. Again, because the tests are not provided, don't change the name of this function, and don't change its signature. So a couple of people on previous assignments, for some reason, changed the signature of the generate function. So they failed all the known good tests. Don't do that. And obviously we need our generator view. With the green ones are the accessibility labels. Remember, this is backslash separated text. Same as we've done, getting very, very familiar with this already, but you need to write your own tests for this. So let me actually just see that. Let's just see that running. So this is the model solution, usual thing. Right, good to go, clear, and so on, and all this kind of usual good stuff in the calendar generator. But you need to write your own tests, and you do need to get perfect code coverage. But as we saw, it will produce that for you. It will produce it really quickly. Whenever you do npm test, it will tell you what the code coverage is. And if it's less than 100%, you can open that HTML file. Over here on the right, in this empty spot, because this is the model solution, there are no uncovered lines. It will give you the line numbers. So if you don't want to open the HTML version, you can just get the line numbers and go in and figure out why it's not being covered. And no linter errors. So there's an npm at run lint, which basically is checking that you've written good JavaScript and or good TypeScript. So this is very much the make it work, make it right, make it fast. This is the make it right. So it's not only does it work, passes the tests, and whoops, where did that go? It's well written as well. So the grading is the same as on previous assignments. So the basic bit where we get given the test, that's only worth 30%. But if you get perfect code coverage whilst doing that, that's obviously 60%. And then you add in your advanced features, adding in your tests as you go. And strong recommendation as you go into the advanced part is that you do test-driven development. One test, a little bit of implementation, get back to 100% code coverage. Another test, a little bit more implementation, get back to 100%. Don't try and do the whole advanced thing, then try and get perfect code coverage. This is a really, really simple application. You could probably do that. But it's a bad habit to get into. You absolutely cannot do that on anything that's more realistic. It's definitely going to be a problem once you're actually getting into assignment 9. So get in the habit now of just a little bit, raise your game, always be at 100%. Okay, so that'll do us for today. On Thursday, obviously, we'll be looking at assignment 8, where we need to look at navigation within a React Native application. And on Tuesday, we'll be looking at assignment 9, and then we'll need to know how to do network access and also more complex models that we can respond to in a wider scope throughout the application. So you know what 8 and 9 are going to be. They'll just be the React Native versions. Alrighty, 11 o'clock, that's not too bad. Any questions? Outstanding issues? So if your assignment River was 5, so it crashed and burnt, I noticed a bunch of emails came in this morning. That's great. That'll be on my list to take a look at. It's not necessarily, in some cases, it'd be something you did, which we'll try and fix. In some cases, it won't. As we've seen from our own work, Xcode is an interesting, what's the word? An interesting environment. It doesn't always work. Yeah, question. Yeah. Oh, yeah. So I think that question is probably why doesn't it return me as a member of Workspaces? Is that the question? Come in the chat. Yeah, so basically I'm a member of every workspace. Yep. It's because I'm kind of a super user. It's so that you can't delete me. Yeah, there's a bit of logic in the API. Basically, if you add a member, and yeah, oh, should do. Anyway, but it's if you've got an issue in terms of testing, look at so in your tests, add a new member, make sure it's there, delete that member, make sure it's gone. So don't worry about the one. If the things are not coming back, bug, it's designed so that I don't come back. Didn't realize it wasn't doing the other ones. But in your tests, um, create a new member and add a new member to the workspace, and then or two or three, whatever you want. And then obviously you need a test to swipe it and delete it and make sure it's gone. Yeah. Okay. Yeah, but you have the ability to prove that your adding members works, and the ability to prove that you're removing members works. Yeah, that'll be fine. Okay, good stuff. So if you send me the email, we'll work through those assignment 5 issues. As you can tell, the sort of lecture bits are tapering off because we're based on understanding that we've already got from Android and iOS, which gives me more time to have a look at the 2, 3, and 5, what was going on there. Okay, good stuff. Oh, so yeah, the Android ones, I haven't come up with any good explanation for why so many are failing. What I'm probably going to do is look at the assignment fives first, because they're probably going to be easier to identify the problems, and then go back and start looking at the Android ones. Yeah. So yeah, Peter. So yeah, it's basically the sequence I'm going to be doing them in is going to be 5, 3, 2. Yeah, so I'm going to do the 5 ones first, then have a look at 3, and then at 2. The only guarantee we make for manual regrades is that they're done by the end of the session. So that's a week on Friday. They all always get done. Alrighty, good stuff. So if I don't see you in office hours today, we'll see you back on Thursday. Make use of Veshmail's office hours today. If you've still got last minute questions about assignment 6, and of course anything about assignment 7 once you've got that installed. Even if you're working on assignment 6, it's not a bad idea to install assignment 7. Just make sure that you can get the starter code up and running, in case you have a question on that. Oh yeah, model solutions. No, the assignments change slightly year to year, but the real reason we don't give out model solutions is because subsequently all the submissions look exactly like the model solutions, which is not what we want. We want you to come up with your own way of doing it based on the examples. So if you like, the example codes that we give you are the model solutions. Yeah. Yeah. A test case. Okay, so this is the thing, is that what we're actually doing is really we're testing your ability to write test cases. So we give you some to show you how they work, and then it's okay. Now you know the mechanisms of writing a test case. Let's see how good you are at writing test cases. So if your test cases pass, but you don't pass the known good ones, what that means, and this is a really great question, so thanks for asking it. And what that means is that you've tested what you wrote, which sounds like a good thing, but it's always a bad thing. We want to write what the test demands we write. And that means if the test is good, in other words, we wrote a good test, implicitly the implementation is good. What tends to happen is if you do, what always actually happens, if you do implementation first and then a test, is you test your implementation. Because you wrote the implementation, you know what it does, so you test what it does. Whereas if you write the test first, you're laying out your stall and saying, this is what I want my app to do. I don't know and I don't care how it does it. I just want it to do that. And then you write the implementation to pass the test. Yeah. So again, really, we're testing your ability to write tests. Yeah. Mhm. So but then it's a great question again. So the English language or any natural language is enormously imprecise. That's just the way it is. We fill in the gaps between it, which is why we give you, screenshots and information about how things should actually work. So a customer is telling you what they want, and giving you as much information as they can, in good faith. But importantly, for instance, if a customer tells you we want the starter screen to look like this, and they give you a screenshot of it, what they're saying is we want it to look like that immediately, for instance, not some point in the future. So if you've got an implementation that lazily implements that user interface, and your test allows that lazy implementation, that's probably not what your customer is asking for. But specific cases, bring them along to office hours, and we'll actually take a look. So if you had great code coverage, you had loads of tests, your code coverage was awesome, but you failed a couple of the known good tests, by all means, wander along to office hours and we'll have a look at where your tests weren't quite up to scratch. Because that's the important issue. It's not that there's something wrong with your implementation, it's there's something wrong with your tests. So as we become better at this, the mark of a great engineer is how good they are at testing. Programming is easy. Testing is actually significantly more difficult because of that disjoint in between natural language and code. Yep. But anyway, come on. If you fail a test, an ungood test, you think, pretty sure I had a test for that. Wander along and we'll do a comparison. And that there's a lot of learning to be taken from that comparison. Ready, good stuff. So if I don't see you in office hours, back here on Thursday. And great marks on the quiz, by the way. That was all good stuff. And remember the cross-platform quiz will be on a week on Thursday, the last day. Alrighty. Oh yes, there's office hours today. Yep, yeah, your normal ones at 5 o'clock. Okay, see you then. Bye.